My pleasure to introduce the speaker. From perhaps the 1960s onwards into the 1990s, one of the big streams within the broad subject of topology was geometric topology. And it's still alive, but not quite the prominence that it had in those decades. From the 1990s until now, a sort of a closely related area known as geometric group theory has sort of become very popular and with very interesting mathematics, and is in some sense a natural sibling of geometric topology. It's quite hard to find people who really have a major reputation in both. Our speaker today, Craig Guilbault of the University of Wisconsin-Milwaukee, is not just such a person, but he's the first name that comes to mind when one is looking for that combination. It's a pleasure to introduce him.
Okay, so thanks a lot for that nice introduction, Ross. I would have to say, without Ross's writings, and in particular his book, I don't think it would be possible for me to have sort of made that step to bridge between geometric topology and geometric group theory that I like to strive for anyway. I'd like to also thank the organizers of the conference. I feel really honored to be up here in front of all these mathematicians who I have so much respect for. So thanks a lot. I'm going to try to give this in the spirit of a genuine plenary talk, and then I'm going to keep things fairly basic and show you a lot of pictures, not very many proofs at all, but hopefully to give you kind of a big picture of one point of view of geometric group theory. And you will definitely see that when I try doing geometric group theory, I rely on what I know about geometric topology. And so I've really enjoyed seeing in the last several years a lot more of this old style geometric topology playing an important role in geometric group theory. And I think the study of boundaries of groups in particular is one area where that's really prominent. And for people who have expertise in working with complicated topological spaces, this is an area to look into. It's there seems to be a lot going on now, and it's a fun topic. Okay, so I want to give the talk some structure. I decided I wanted to sort of focus on two of my favorite problems in geometric group theory. One I'm going to call the semi-stability conjecture. Ross called it the problem earlier, but at one point in time I was able to get him to agree to let me call it a conjecture, even though he said it was really only a question. But it's been around for an awfully long time, and I think at some point it's safe to just call it a conjecture. So this one says every finitely presented group G is semi-stable at infinity. Some of you have seen this problem discussed already. You know exactly what this means. For a lot of you, I'm sure those words mean almost nothing, and one of the goals of my talk will be to explain this gradually. So if you don't understand it now, don't worry. Part of the talk, a big part of the talk, is to just help you understand what that problem is and why I think it's a pretty interesting and worthwhile problem. The next one I'm going to call the group boundary question. This will eventually become a conjecture, hopefully. Well, unless somebody solves it. Does every type F group admit a Z boundary? Again, some of you know exactly what that means. Some of you have no idea. But part of my job will be to help you understand what that problem is all about. And Besvina is the one who posed this question. There were variations on this. One of them, in fact, that Ross is responsible for also. But I think it's safe to say that Besvina is the person who really identified this as a hard and interesting question. Okay, so in the spirit of trying to help you understand these, first I want to tell you what a type F group is. So one way to define it is a group is type F if a group G is type F. F just stands for finite. And what that means is there's a finite KG1 complex. So in other words, there's a finite CW complex K, which has G as its fundamental group, and all of its higher homotopy groups are trivial. Okay, equivalently, for that complex K, it's got the right fundamental group, and when you pass to the universal cover, it becomes a contractible space. Okay, so that we're going to see is going to play a pretty important role in what we're doing here. Now, you don't really need to talk about fundamental groups at all. You could just say, okay, a group is type F if it acts, if there's a nice action of that, if there's an action of that group on a nice space. So the action is supposed to be a proper action, an action of a group on a, now these are going to be infinite groups in general, but a group action is proper if whenever you take a compact set and start moving it around with the group elements, that only finitely many of those translates will actually intersect your original compact set. So think of it when we start letting the group act on the space, compact sets get pushed out off of any existing compact set. Freely means no fixed points, so that's a fairly simple condition. Co-compactly just means that the quotient space is compact. Alternatively, you can say there is a compact set so that you can move it around with the group action and cover up the whole space with that. Those are equivalent in the sorts of spaces that I'm interested in here. And I want the space to be nice. And so what I'm going to say here is a proper metric absolute retract, AR. Let me say a little bit about that, because even people in geometric group theory might not often think this generally. Proper metric just means it's a metric space, or at least metrizable, and every closed ball is compact. That's what proper means. The AR stands for absolute retract, which goes back to this sort of topology Ross is talking about. But it really means a space which has nice local properties. If you just think about local contractibility is the most notable property of this. So lots of these if you're specializing in bad spaces, these are not where you want to look. These are spaces, as I said, local contractibility is sort of the key property. But what I like about this category is people doing geometric group theory are sometimes manifold topologists, sometimes they work in cat-0 spaces, sometimes they work with CW complexes. In this AR category is one that is one broad category that covers all of those different cases as just special cases. And you can often, if you work hard enough, give a single proof that doesn't require that you use those individual properties. And so AR, I think, is the right place. Now, there's also ANR, absolute neighborhood retract, means the same thing, except that an AR has to be a contractible ANR. And we want these things, our groups, to be working on these contractible spaces. Okay, so type F groups, remember, so if I just draw pictures, these are representing groups that I have in mind. The line, remember, I want my groups to act in this nice way. And so you see the line, and you can think of that as the covering space of the circle. So the line is the space I would associate with the infinite cyclic group. To the right, that's supposed to represent the plane. So if your group is Z plus Z, then this would be this would be an AR. It's got all these nice properties. And the group Z plus Z acts properly, co-compactly, and freely on this. In other words, it acts by covering transformations. That's another way to say that. R3, you see 3 space, well, there's a group that's associated with that. And then on the lower right-hand side, that's supposed to represent the universal cover of the figure 8 space. So the free group on 2 generators acts in that nice way on this space. And even though that space is a little bit exotic, it is an AR. Notice it branches off infinitely, but there are no bad points. Locally, that space is very nice, and certainly it's contractible. So this is how we would study groups, is we'd look for a space first, and then we'd start studying the space together with the group action. Okay, so some other examples of type F groups. So all those groups I mentioned are type F because I just mentioned that they act nicely on those contractible ARs. All free groups and all free abelian groups are type F. They have to be finitely generated because, remember, I want a compact KG1 space. All surface groups, surfaces are covered in general by a space homeomorphic to the plane, except for Z2. Well, there's the two-sphere also, but that's the trivial group, and it acts on a one-point set, so it's really just the Z2 you've got to toss out. In fact, fundamental group of any closed aspherical n-manifold, aspherical just means all the higher homotopy groups are trivial, and once you know that, you know the universal cover then is contractible. So this is one of my favorite classes of groups because it branches these two areas. People in manifold topology are very interested in aspherical manifolds, and people in geometric group theory tend to like to study these groups as well because they act on these very nice spaces. Torsion-free word hyperbolic groups. If there are any of these in the list that are not familiar to you, don't worry about it. I'm just giving you a lot of examples now. But most of you probably know what hyperbolic groups are in the sense of Gromov. Torsion-free cat-zero groups. Baumslag solitaire groups, I put that in there because they play a role in this talk, and some of you have seen Molly Moran give a nice talk on these groups related to the topic that I'm speaking on as well. And then another nice thing is you can take free products or direct products and a lot of kinds of extensions of type F groups to create more of them. So once you've got those first 6 categories, you can use those to create a lot more type F groups. I've invented a symbol type F star groups because that requirement that the action be free is sometimes more than you need. For example, I had to say torsion-free cat-zero groups, torsion-free word hyperbolic groups, and it's all I really need to do is throw that condition away, and almost everything I do is still going to work anyway. So I've, at least for temporary purposes of this talk, invented this notion of a type F star group, which is one which acts properly and co-compactly, not necessarily freely. So then you can have all cat-zero groups, all hyperbolic groups, but you can also now, you don't have to throw out the finite groups now. They act on a one-point set. Not very interesting, but that still allows you to, well, here Coxeter groups, very favorite topic of people in geometric group theory. Nice to not have to toss those out. And then free and direct products. So you can take, any of the groups on the previous slide and take its product with a finite group, and now it's still okay to work with that one if I say type F star. Okay, so in particular, the group boundary question from the first slide, which some of you still are waiting to find out what that means, applies equally well to groups of type F star. And I mentioned a paper that I wrote with Molly Moran just recently that's appearing in Expositiones, which sort of explains why you can get away with this in this very broad context of ARs. Okay, so the big idea of geometric group theory then is to study the group by studying the space together with the action. And so again, I return to this same slide where we've got these different spaces, and the fact that these spaces are different from one another is what we're going to use to maybe distinguish the groups that are acting on them. Now, if you were to give these spaces to a class in algebraic topology and say, well, explain to me why they're different, well, they're all contractible, so that's kind of a bummer when you think of all the homotopy and homology invariants that you learn. They're sort of useless here, or at least they seem useless at first. What I'm going to convince you is that actually by approaching these things appropriately, a lot of those algebraic type invariants that you've learned about can be put to use in this context as well. Okay, this is going to be an important concept when you're studying non-compact spaces, the notion of a proper map. is important. The definition can be made very simple. A map is proper if the preimage of every compact set is compact. Okay, and then we can define what it means to be a proper homotopy equivalence. That means that there's a map going in the other direction so that the well, the definition is going to force that map to be proper as well, but the real definition just says the compositions, as usual, are homotopic to the identity, but now we want to say that those compositions are properly homotopic to the identity. That means the homotopy has to be a proper map as well. Okay, and so the theorem that is very crucial for us is that if you have a type F group and it acts in this nice way, properly, freely, and co-compactly on a pair of proper metric ARs, so same group acting on two possibly very different looking spaces, well, they may look different, but they have to be proper homotopy equivalent to one another. So that's going to give us some sort of well-definedness for choosing. If I give you a group and you have to choose a space for it to act on, you may all choose different spaces, but they're going to be properly homotopic, proper homotopy equivalent to one another, and that's going to be a very useful fact. The proof of that is just covering space theory. You could probably figure it out. It's not a real easy proof to write down, but the idea is very simple. I don't think I'll talk about the proof, but one problem going from groups of type F to F star is all of a sudden the quotient map is not a covering map, and you have to figure out how to do all these proofs without using covering space theory. So they're far from impossible. In fact, as I said, Molly and I, the reason that paper appears in Expositiones is we wanted to put in lots of detail for people who might otherwise be sort of put off by some of this general topology terminology, and show you that actually this is pretty easy and very natural stuff. So I would encourage you, if you've never heard about ARs or ANRs, you don't want to try to pick up a book and read the whole book, but we tried to write a little expository paper that has some interesting theorems in it, we think, but which also introduces people gently to that sort of topology. Okay, so I was talking about proper homotopy types. Here's an example. These pictures come in two pairs. The top two spaces, if your group is the infinite cyclic group, perhaps you chose the circle as your KZ1, and then the line as your universal cover, but maybe you chose an annulus, a closed annulus, because it's supposed to be compact. And then the spaces you're acting on are the line and that's supposed to be an infinitely long strip. And they're not the same, but they are proper homotopy equivalent to one another. Notice it's clear. All these spaces I'm talking about are homotopy equivalent. They're all homotopy equivalent to a one-point set. But proper homotopy equivalence is a little bit finer. So you can see how you could squash that infinite strip down onto a line in such a way the preimage of every point is compact. And so you're kind of on your way to seeing why that's a proper homotopy equivalence. On the left-hand side, I chose the figure 8 for my Z star Z group. Somebody who likes to do differential geometry might have chosen some sort of truncated punctured torus and got a much more interesting looking space, but they turn out to be proper homotopy equivalent. In fact, I've drawn that snowflake space in red inside there, and again, you could actually squash the right-hand space down onto the red in such a way that preimages of compact sets are compact, and so you have this proper homotopy equivalence. Okay, so I want to talk about ends of spaces. So that's one of the differences between some of the spaces I've looked at is even though they're all contractible, you can make sense of how many ends the space has. Like a line has two ends. You can go out in the positive, negative direction, whereas R2, the plane, really just has one end. It's a bigger end, but there's only one of them. And so this is to make precise sense of that. What you do is you first fill up your space with larger and larger compact sets, And then you look at the complements. You're actually interested in what we call neighborhoods of infinity, which just by definition are complements of compact sets. And so really it's the second bullet point I'm interested in. I have this nested sequence of smaller and smaller neighborhoods of infinity. Saying it's cofinal means if you intersect them, there's nothing left. So you want, since the CIs exhaust the whole space, then the intersection of the neighborhoods of infinity is empty. And then what you can do is just go look at those neighborhoods of infinity and count how many components are in them. Or better yet, you should ignore the compact components and you should count the, let's see. Yeah, I should have said unbounded components, those with non-compact closure. And that number is going to, it might stabilize, but it's never going to go down, because when you cut off a smaller neighborhood of infinity, each of those components is going to be contained in one of the previous ones. You might get more, or you might get the same number, but you'll never get less. And so the number of ends of your space is just the maximum that you get out of this sequence, and possibly infinite. So if eventually that sequence of integers stabilizes at n, you say your space is n-ended, and if it keeps increasing, you just say your space is infinite-ended. Okay, and the key fact here is that proper homotopy equivalent spaces will have the same number of ends. Okay, I gave you two pairs of examples. That might not exactly be a proof, but it's not a hard thing to prove. Okay, so I think I sort of sloughed over this. Okay, so I guess not. Going back to where I said that if a type F group acts properly, freely, co-compactly on two different spaces, they have to be proper homotopy equivalent, and so they have to have the same number of ends. So we can define the number of ends of a group, pick your favorite space, and count up the number of ends. And this is actually, for people who do geometric group theory, this is a common thing that you hear said. How many ends does your group have? And this is going to be a perfectly good way to use topology to distinguish between groups. You might be a little disappointed to find out that every group is either zero-ended, one-ended, two-ended, or infinite-ended. So you're not going to get too fine of a distinction. You're not going to divide your collection of groups up into too many collections just with this invariant, but it's a start. And this is surprising. You can say surprisingly much. First of all, it's zero-ended. Your space is compact, so the only type F group that acts on a compact AR is the trivial group. If your space is two-ended, you have the integers here. That's all that you could have. And if it's infinite-ended, so these are if and only if in all three cases. Infinite-ended, if and only if it's a non-trivial free product of two other groups. Two other type F groups. That's actually important. And so a couple remarks is, well, this sort of gets out of the way all except the one-ended groups. Zero-ended, two-ended, we've already settled things there. Infinite-ended, well, you can split that infinite-ended group into smaller groups, and you can keep doing that until hopefully you're down to only one-ended groups. And so that should allow you to focus your attention mostly on one-ended groups. There is a version of this for type F star, but all these statements are true, but with a lot of extra terminology needed, so I just decided to avoid that by focusing on type F. And in fact, you don't really need F star either. You can say just for finitely presented groups here, and you get pretty much the same theorem. But then there are other technical issues about why these things are well defined, which I just decided for this talk was more general than I wanted to get. Okay, why can't you have a three-ended group? What I've tried to indicate here is a three-ended space. Why can't you have a group that acts properly, freely, co-compactly here? Well, I thought there should be at least one little proof in this talk, so let's see if we can do it. The fact that it's three-ended means you can take this compact set, which has exactly three unbounded components, and if it were really three-ended, no matter how big that compact set would be, you would never get more than that. Okay, but remember now, there is a group action which is going to take this compact set and completely move it off of itself. So I've backed up now and looked at the space from a bigger distance, and now notice that I have translated that compact set up into one of those three ends. The red set is connected, so it's got to lie inside of one of those three pieces, but now it also has the property that it separates the space into itself in three unbounded components, and the other red set has to lie in one of those. And so now I'll just leave it to you to fill in the details to convince yourself that if you take the union of those two red sets, there have to be more than three unbounded components. You can see them in the picture. And now you could also use the same argument to explain why you can't have a four-ended or a five-ended or a six-ended group. Okay, foreshadowing, I wanted to go back to talking about how many ends your space have and give an alternate approach to thinking about counting up the number of ends. And that is to build an inverse sequence. After all, we were just counting the number of components, right? We've got a sort of an algebraic tool for that, which we call pi zero of the space. It's just got one element for each component. And now a smaller neighborhood of infinity includes in, so you have an inclusion. It's not a homomorphism here, these aren't groups, but it's an inclusion-induced map from pi 0 of n1 into n0 and so on. And if you take the inverse limit of that, you can call that inverse limit the ends of x, or you can associate the ends of x with the points of that inverse limit. Okay? Here are three spaces that are infinite-ended. Before, it's always said is either it has finitely many ends or it's infinite-ended. This is actually a little bit finer because if you think about the inverse limit you get from the space on the left-hand side, it ends up being uncountable because every one of those bonding maps has at least, well, if you choose things carefully here, it's going to have 3 points coming in. So it splits, a point splits off into three, each of those splits off into three, and your usual business, you can sort of see that that's going to be some sort of Cantor set. Whereas the middle picture and the right-hand picture, you can convince yourself there are only going to be countably many elements in that inverse limit. You might ask yourself, well, what about the pictures, the two right-hand pictures? Are they proper homotopy equivalent to one another? They both have the same number of ends. Neither of them is going to allow one of these nice group actions. But it's still a good question whether those are proper homotopy equivalent to one another. We'll talk about that again later. Okay, so now what I want to do, though, is return to this method, taking my space. Perhaps it's even a one-ended space now, so what I just did would not tell us anything, but remember, we're interested in one-ended spaces now if we're studying groups. And so instead of applying the pi 0 functor, just apply some other functor like the homology functor. Create the same inverse sequence, and this is what you would call the pro-HK. Somehow that space became a Y. I think it was supposed to be X. But you have this inverse sequence of homology groups, and this is what we would call one of the end invariants. You might do, instead of homology, you might do the homotopy groups. Things get a little bit interesting here because I have to choose base points now, and that's a little bit tricky. All of those bonding maps in the middle line are just induced by inclusion. I want to say the ones in the next row are induced by inclusion, But there's no way you can pick one endpoint that's going to work for all of those neighborhoods of infinity. So you're forced to choose infinitely many base points. And that caused us a little bit of a trouble. That's why the R appears in, I see I have Y there also. The R stands for not a base point, but a base ray. And what we do is we choose a ray that runs off to infinity, and then we choose the base points. We require they be chosen to lie on that ray. Okay. And the ray comes in handy for another thing, and that is we have to do a change of base point isomorphism in there as well, and we just make sure that we choose the path to be a segment of that ray. Now, there is one issue that might come to mind, is that two of you who are doing the same problem might choose two very different sequences of neighborhoods of infinity, so your inverse sequences might look very different. So we have to put an equivalence relation on them, which we call pro-isomorphism. This gets a little technical, but two inverse sequences of groups are pro-isomorphic if they contain subsequences that can be fit into a commuting ladder diagram like this. And it's an easy exercise to convince yourself that you can do that if you have two different sequences for the same space, but with different choices of neighborhoods of infinity. So that's the first thing I said. So right then, if you say that pro-HK is the pro-isomorphism class, then you've got a topological invariant here. And similarly for pro-pi-K, except that you've got this base ray, you better choose the same base ray both times. A very useful lemma is that if you have two different base rays, did I miss something here? I guess that must be later. If you have two different base rays, as long as they're properly homotopic to one another, then you can use either one. They're going to give you the same results. You would really hope, well, this is just analogous to the change of base points isomorphism that you learn in a basic topology class. And so, in fact, we can go further then and say that these inverse sequences that I was talking about are proper homotopy invariants. Not just topological invariants, but if two spaces are proper homotopy equivalent, then their pro-HKs and pro-pi-Ks are going to be pro-isomorphic to one another. This is true basically because proper maps send neighborhoods of infinity into neighborhoods of infinity, and with a little bit of thought, you'll convince yourself of that. But if I want this to be true, I have to make sure that I pay attention to the base ray again. The base ray I use in Y better be the image under that proper homotopy equivalence of the base ray in X. Okay. This base ray is actually great when you have a multi-ended space, because if you want to measure the fundamental group in one direction, you just choose a ray in that direction, and maybe you want to measure the fundamental group of a different end, you choose the ray to go into that end. So this is actually a good thing sometimes, but unfortunately, when you have a one-ended space, it still matters which base ray you choose. And I've given an example of a space which is just what you call an infinite mapping telescope. The maps are just 2-to-1 maps of the circle to itself, and you just glue an infinite string of mapping cylinders. And it turns out that there are uncountably many different proper homotopy classes of rays that go out to infinity here. And so, not necessarily for this example, but in general, when that happens, pro-pi K might not even be pro-isomorphic when you choose different rays. In fact, some of you might be sitting there saying, why don't you just take the inverse limit of that inverse sequence? That's a good idea, except for the fact that you sometimes lose information. But even in this situation, those inverse limits might be different depending on which base ray you chose. Okay, so now I want to say, let's talk about end invariance of groups. I sort of gave you a lot of warnings, but let's, for one thing, none of those apply to homology because you don't have to worry about base points, so we've got some nice end invariance. And even for homotopy, don't give up on it yet. Don't throw it out just because I've pointed out some of the technical problems with homotopy invariance at the end. So, okay, so what I want to do now is I want to define the end invariance of a group. And so it's going to be, for this talk anyway, it's going to have to be a type F or a type F star group, because then I can tell you, choose whatever space you want on which that group acts properly, co-compactly, freely, and then do what we just did. Measure what that space, those spaces are contractible, so I said there's no algebraic invariant, but if you look at the ends, those same old algebraic invariants can be quite handy for you. So the number of ends can be thought of now as an invariant of the group. Just count the number of ends in whichever space you chose. Guaranteed two people with the same group are going to get the same number there. Pro HK of the group means pro HK of the space that you happen to choose. And pro pi k of G is, well, there's this base ray problem. It'd be nice if there was a canonical way to choose the base ray. And so, at least right now, I can't really tell you that that's a nice group invariant. This is where one reason the semi-stability conjecture is such an intriguing problem is the semi-stability conjecture says this. In a one-ended group of type F or F star, or in fact it's more general than this, any two proper rays in the space you chose have to be properly homotopic. That seems unlikely given the very simple picture I showed you before where there are uncountably many, but that space, even if you cone it off and make it contractible, that cannot be the universal cover of some compact space. Okay, so all of the examples for which you have lots of different proper rays to infinity, none of those that people have found out yet have been universal covers for finite KG1 complexes. So it's still hopeful that maybe you don't have to worry about base rays at all, at least when you're studying groups instead of just spaces. So this is a different way of thinking about the semi-stability conjecture than maybe some of you have seen it before. We were talking earlier this week about pushing circles out to infinity. This is an equivalent formulation of the semi-stability conjecture. What are some uses of these end invariants? Well, we can distinguish Rm from Rn. Maybe that doesn't sound like much of an accomplishment. Not by counting the ends, but if you want to distinguish R2 from R3, you could use second homology at infinity, for example, or third homology at infinity, or you could use pi2 and pi3, because in Euclidean space, it's pretty easy to prove that any two proper rays are properly homotopic, so those are perfectly good invariants there. On a more technical note, pro-HK actually can be used to calculate certain group cohomology with ZG coefficients. This is something that can be defined completely algebraically, but what this does, it says, well, this is really the geometric meaning of some completely algebraic invariants, or ones that can be defined completely algebraically anyway. And even the fundamental group at infinity, where you don't always know that it's well defined, there's enough information there that you can use it, and it's been used for things like, characterizing Euclidean space, distinguishing it from other contractible open manifolds. If you've seen the Whitehead manifold, that's one way to prove it's not three-dimensional space, is by proving it's not simply connected at infinity. Stallings has a very important theorem that says it's all you need to know is that the fundamental group at infinity is essentially trivial, and you've got Euclidean space. The Davis exotic universal covers, you can prove they're exotic using pro pi 1. Won't go into that too much more. And another way of talking about semi-stability is that when you write those inverse sequence of pi 1s, that that's equivalent to an inverse sequence of surjective homomorphisms. So that's yet another way you might see somebody talk about the semi-stability conjecture. Looks very different, but it's equivalent. Okay, so I would like to now shift over to the other question, which is these boundaries. What do I mean by a Z boundary? Well, first of all, let's do a warm-up part. Recall that when we define the ends, essentially that inverse sequence approach, we found 1 point for each end of the space. And we just counted up how many elements in that set. Well, instead of just counting those, what we can do is we can glue 1 point onto our space for each element of that set. And we can use that set to actually get what's called the Freudenthal compactification. So I've resurrected those 3 spaces before. On the left-hand side, you have to add an entire Cantor set for this compactification. And recall, I was trying to get you to decide whether you thought the 2 right-hand spaces are proper homotopy equivalent. Well, the red points, the points we added, they now have a topology on them. We can call that the Freudenthal boundary. And notice that in the middle space, you're going to have exactly 1 special point that's a limit point. But on the right-hand space, you have 2 special points. All the other points are isolated. So that actually is a proof that those 2 spaces are not proper homotopy equivalent to one another, even though they're both contractible and they both have the same number of ends. So by bringing a little bit of topology into the theory of ends, you can get a little more information from that process. That's sort of what Z compactifications are all about. The idea is we're going to, instead of just defining algebraic invariance of the end of a space, we're actually going to try to do a compactification which captures all of what's happening at infinity. There's a special sort of compactification using something known as Z-sets. These were invented by R.D. Anderson back in the 60s or 70s? 60s. End of the 60s. Okay, so a subset of a space Y is a Z-set if whenever you throw away that subset, you don't change the homotopy type of the space at all. In fact, for any open subset of the space, you throw away the part that lives in A, and at least homotopically speaking, you don't notice any difference. We had some discussion earlier. Z is for 0. It's like a set that has 0 impact on the space when you throw it away, at least up to homotopy. And then I think the first place I saw people using this idea for getting a nice compactification was Chapman and Siebenmann in '76, where they defined this Z compactification to be what you think it is. It's a Z compactification if the stuff you add on is a Z set. Of all the different compactifications, beginning with 1-point compactifications up to stone-check compactification, somewhere in there, this type of compactification plays a pretty important role. So here are some examples. There are 4 spaces I had up before. For the line and for the snowflake, the endpoint compactification is already the Z compactification. Or sorry, the endpoint compactification. But if you did the endpoint compactification to the plane, it would be the 1-point compactification, and that would drastically change the homotopy type of the space. And so instead we add a circle onto that, and now if you think about the definition, no problem. And for 3-space, we add the 2-sphere to that. That's what that's supposed to represent anyway. Okay, so motivated by some examples that were already out in the air, in particular cat-0 and hyperbolic groups, Besvina decided this was the right way to give a general abstract definition of a group boundary. Dernishnikov came along and generalized it a little bit, and then Molly and I kind of came in and polished up some of the issues that made Dernishnikov's definition, it cost Besvina some of his theorems if you change definitions, and we came back and were able to show that, in fact, you might as well go with the general definition of Dernishnikov. So let's just get that definition up there. If you want a Z structure on a group, you should start out as usual. It should be a type F group, or at least a type F star group. Choose your space, and then get a Z compactification of it. And now you're most of the way there, but Besvina tossed in another condition that said that, in addition, in this compactification, when you start moving a compact set around, you can push it out towards that boundary. It should get smaller and smaller. You can put a metric on the compactification, choose whatever metric you want, actually, and then push that compact set out, and you would like those sets to become small as you go. Okay, so then we call this a Z boundary for the group. You can throw away condition 3 if you want and just call it a weak Z boundary. There's still a lot of good information there. Or you can add another condition, which a lot of geometric group theorists naturally want, and that is they would like the group action to extend to the compactification. And we call that an EZ structure for an equivariant Z structure. Okay, so the interesting thing is, sort of like we could use that Freudenthal boundary to tell us extra information about the space, even if you just have a weak Z boundary, if you only knew the boundary, you would know the proper homotopy type of the space in the context of contractible ARs that we're working on here. Okay? For those of you who know what the word shape theory, or what the phrase shape theory means, the end invariants of the space actually agree with the shape invariants of the boundary you added. So this theory was just sitting there waiting to be used, and I think it was fortunate that people like Ross and Mladen Besvina were very familiar with this, and they saw how it could be used in geometric group theory. The group cohomology with these ZG coefficients is actually related to those shape invariants of the boundary. The nullity condition puts even more, it sort of forces you to pick what Besvina views as the better sets of boundaries. It makes the actual topological dimension an invariant of the group. And in fact, that dimension is the same as the cohomological dimension, except for a shift by 1. If you can put an EZ structure on a group, you've solved a very important problem called the Novikov conjecture for that group. And so people like Tom Farrell and Jean Lafont and Steve Ferry, Shmuel Weinberger, lots of people like that work hard on the Novikov conjecture. And this is one approach you can take towards working on that problem. These two problems, well, so the Z boundary problem, of course, is does every type F group admit a Z boundary? There's a relationship between the semi-stability problem and the Z boundary problem. If you can put a Z boundary on it, the topology of that boundary also tells you whether the semi-stability problem is, whether the semi-stability conjecture is true for that group. If your boundary is locally connected, the reason it's a squiggly line is actually, I should say, if that boundary has the shape of a locally connected space. But not to get too deep into that, but there's the nice connection between those. So finding Z boundaries is sometimes an effective way of attacking the semi-stability conjecture. So here's the group boundary question. Does every type F group or type F star group admit a Z boundary? And you can also ask, it's unknown for even weak Z boundaries, and it's certainly unknown for EZ boundaries. So take your pick if you want to work on that problem. So here's some examples of group boundaries. Well, remember, I associate a group with each of these spaces, so these are not only Z boundaries of spaces, they're Z boundaries of the associated groups. For those of you who like to work with weird spaces, now is where the weird spaces come in. Even when the space is really nice, boundaries are really exotic and interesting spaces. So the Sierpinski carpet is a very common Z boundary for a lot of groups. The Menger sponge or the Menger curve, whatever you want to call it, is also a very common boundary. And on the bottom, I've drawn an inverse sequence. This comes up if you take a manifold and then this is sort of like an infinite genus surface. You punch a hole and you sew in another surface, and then you punch holes and you sew in more. So let me not dwell on that construction. You get something called a Pontryagin surface. And again, it's a fractal, fractal-like objects are very common as group boundaries. So if you've got expertise in that area, then this might be a topic that would interest you as well. I thought I'd mention some positive results. All cat zero groups have Z boundaries. Those were sort of the original ones. It's just the visual boundary that you glue onto your cat zero space. Hyperbolic groups, this is where it got really interesting. Gromov defined the boundary from a completely different perspective, and Besvina and Mess came along and said, actually what they're doing is they're Z-compactifying a certain Rips complex. And that was when Besvina sort of hit onto the idea that, well, you don't need all this geometry. You can just define a Z structure for any type F group or even F star group now. And really what you should be talking about is Z compactifications along with some of the group theory to sort of manage that group actions. The problem of whether all type F groups admit boundaries seems unapproachable. So what's been happening is people have been looking at their favorite collection of groups and gradually adding to the list of groups that admit Z structures. So Osaida and Przicki show that all systolic groups admit Z structures or Z boundaries. Relatively hyperbolic groups, if the peripherals admit boundaries, then so does the group. There are certain complexes of groups with conditions on those groups. Free and direct products, semi-direct products, all three manifold groups. Those last three things on the list are actually quite recent. And I have special interest in those because Brian Peach is a recent PhD student of mine who did, 7 and 8 there. And then Molly and Carrie Terrell and Molly spoke about doing this for Baum's-like solitaire groups earlier. There's some nice candidates out there for next steps. Braid groups is one of my favorite examples. I feel pretty confident that that can be nailed down. One way I like to think about the Z boundary question is oftentimes there are classes of groups that people are trying to prove are cat zero. This is sort of a halfway step there, right? If it's cat zero, it certainly admits a boundary, but you might be able to put a boundary on it without going all the way and proving it's a cat zero group. And so, braid groups is one of those, and a lot of Artin groups fall into that category also. Extensions of type F star by type F star. My student Brian Peach made some progress on that, but I sort of suspect it's true in general, and that would knock off, for example, the braid groups. Of course, the finite type Artin groups would knock off braid groups in a different way. Farrell and Lafont have specifically asked about torsion-free subgroups of SLNZ. Fundamental groups of closed aspherical manifolds. As a manifold topologist, this is the problem I would really like to be able to make some progress on. The hope would be that using manifold topology and all those special techniques, that might give you a little bit of an advantage to getting a Z compactification, but honestly, very little progress on doing a general argument here for manifolds. In fact, there really is no general strategy. All the strategies are to look at the specific class of groups and use specific geometry and go from there. So, that's still pie in the sky to come up with a method, a program for solving this problem. So, I guess that's a good place to stop.
Yeah. You mentioned that theorem about the proper homotopy equivalence.
Yes.
Can we say something about orbit spaces? Do they have the same homotopy type? Or
Oh, in the absence of a free action?
If you go back, please.
Yeah,
So
yeah,
you're-
no. So of course, if the action is free, then the answer is yes, that the quotient spaces will, they will be KG1 spaces with the same group, so they're homotopy equivalent.
Yeah.
They're compact and homotopy equivalent. But if the action is not free,
free.
I don't really know what, I don't know what can be said about the quotient spaces.
So the theorem was for F groups or F star groups,
Well,
or free or not free. The theorem was
the theorem about the proper homotopy equivalence of the ARs, that works for type F star groups.
F star.
But as far as, if you wanted to say something about the quotient spaces, then I don't
you.
know unless it's type F instead of F star. That's one of the places where type F is much nicer to work with than type F star.
Other questions?
I apologize that this question isn't more directly relevant to Z structures and ends of groups, but it's something I've been wondering for a while now. What do you think is the future of geometric group theory with respect to its relationship to the broader topology community?
Oh, gosh. Well, it seems like geometric group theory is winning, right? There are a lot of people, a lot of stuff going on in geometric group theory, but there are a lot of good hard problems in geometric topology as well. So I like to see more of this cross-pollination going on. I think that, I think there's a potential for a lot more of that. And so I guess that would be my hope for the future, is they thrive together.
Could I perhaps add the sentence that what hasn't happened yet is the great interplay between algebraic topology and geometric group theory, which I think is going to happen in the next 25 years. Other questions? Well, why don't we give a real round of applause for a wonderful talk?